Okay, now let us look into this problem. The name of the problem is forming a magic square, and this problem is taken from Hackering. I've added link to this problem in the description of the video. So let us look into the problem statement. So initially they have defined what the magic square is. So magic square is an Recursion matrix of distinct positive integers from 1 to n square, where sum of the values in any of the row or column or the diagonal of length n is always equals to some constant number or the same number, and they call this number as a magic constant. So our problem is that we are given a 3x3 matrix which is termed as S, and the values in this matrix S are integers in the inclusive range from 1 to 9, and we can also perform this operation. We are allowed to perform this operation, that is, we can convert any digit A in this input matrix to any another digit B in the range from 1 to 9 at the cost of absolute value of A minus B. So basically the problem is that we are given the input matrix S, which is 3x3 matrix, and we want to convert this matrix into a magic square, and we want to do this at a minimal cost, and cost is calculated as absolute value of A minus B. Okay, so and at the end we want to print this cost. So one thing to note here is that the resulting magic square must have the distinct integers in the range from 1 to 9. Okay, so now let us look into a few of the examples to understand this problem better. So consider this input matrix. Now this matrix is not the magic square, right? Because if you see, sum of values in the first row is 5 plus 3 plus 4, which is 12, and sum of the values in the second row is 1 plus 5 plus 8, which is 14, which is not equal, right? Both of them are not equal. So basically this matrix is not magic square. So now we can convert this matrix into the magic square by performing 3 replacement operations. So basically we can replace this 5 with this 8 here, this 8 here with this 9 here, and this 4 here with this 7 here. So basically we did 3 replacement operations, and cost of each operation is 5 minus 8, absolute value of 5 minus 8 for the first one, 8 minus 9, I mean absolute value of 8 minus 9 for the second one, and absolute value of 4 minus 7 for the third one, and this sums up to 7. So we can convert this input matrix into the magic square at cost 7. So now let us look into a few more examples. So consider this input matrix. Now we want to convert this input matrix into the magic square, and that too at the minimal cost. So let us look into how we can do that. So first of all, let us verify whether it's a magic square or not. So it's not a magic square, right? Because if you see, the sum of values in the second row is 7 plus 3 plus 5, which is 15, and sum of values in the third row, which is 8 plus 1, which is 9 plus 5, which is 14. So both of them are not equal, so it is not magic square. Now we want to convert it to a magic square, so, and that too at the minimal cost. So let us see how we can do it. So we can convert this matrix into a magic square by replacing S of 2 comma 2, which is this value 5, to 6, and cost of doing that is 5 minus 6, absolute value of 5 minus 6, which is 1. So output will be 1, and this is the minimal cost. And after doing this operation, I mean after replacing this 5 by 6, you can check all the rows, columns and diagonals, and you'll find that all of them sums up to one same constant value, and hence it's a magic square after that replacement. Okay, now let us look into the another example. So let us consider this input matrix. Now this input matrix is again not a magic square, because the sum of the values in the second row, which is 7 plus 4 plus 5, which is 16, is not equals to sum of the values in the third row, which is 6 plus 6 plus 1, which is 13, and hence it's not a magic square, and we want to convert it into a magic square at minimal cost. So let us see how we can convert it into a magic square. So basically we'll perform 3 replacements here. The first replacement will be at s of 0, 1, which is here. So basically we'll replace this 8 with 9, and cost of doing that is absolute value of 9 minus 8, which is 1. The second replacement that we'll perform is at s of 1, 0, which is here, and we'll replace this 4 by 3, and cost of doing that is absolute value of 3 minus 4, which is 1. And the third replacement will perform here, which is at s of 2, 0, and we'll replace the 6 by 8, and again the cost of doing that is absolute value of 8 minus 6, which is 2. So overall cost is 1 plus 1 plus 2, which is 4, and this is the minimal cost. And you can check that after performing all this replacement, that is after replacing this 8 by 9, this 4 by 3, and this 6 by 8, if you perform sum of all the rows, columns and diagonals, that sum will be the same value. They'll sum up to the same value. So hence after all this replacement, it will be converted to the magic square. Okay, so now the problem is clear, right? That we are given an input matrix, input 3 cross 3 matrix, and we want to convert that input 3 cross 3 matrix into the magic square, and that too at the minimal cost. Okay, so now we'll look into how to solve this problem. Okay, now let us try to see how we can approach this problem. So for that, let us look into the brute force approach for solving this problem. So here I have listed down the steps for solving this problem using brute force approach. So in step number 1, we'll generate all the possible 3 cross 3 matrices. After that, in step 2, we'll check which of all these 3 cross 3 matrices generated in step 1 are forming the magic squares, and we'll store those magic squares in some vectors. And in step number 3, we'll find the least cost magic square, which is our answer, by comparing all the possible magic squares which we generated in step 2 with our input 3 cross 3 matrix. So okay, so these are the 3 steps of the brute force approach. So basically we'll be able to combine the step number 1 and step number 2, and we will be able to implement it using recursion. We'll see how we can do that. And step number 3 is the one which is finding the least cost magic square by doing some comparison, and we'll be able to implement it using some non-recursive code or iterative code. So we'll look how to do that. Okay, so now we have identified the approach. Now we'll look into the recursion tree. Okay, so before looking into the recursion tree, let us take one step back and let us look into all the possible 2 cross 2 matrices. So here I have drawn all the possible 2 cross 2 matrices. So there is one observation that is to be made here. So if you flatten all these matrices, that is if you read all these matrices in this order, that is from left to right and from top to bottom, or in other words, if you flatten all these matrices and put all of them together, what you will obtain is all the permutations of 1, 2, 3, 4. So the observation here is that you can obtain all the 2 cross 2 matrices by obtaining all the permutations of 1, 2, 3, 4 and then arranging them in particular order in the 2 cross 2 matrices. So this idea can be extended. So if you want to generate all the 3 cross 3 matrices, then what we can do is we can generate all the permutations of 1 to 9, that is numbers from 1 to 9, and we can arrange them in particular order in the 3 cross 3 matrices. So this step 1 here, that is to generate all the possible 3 cross 3 matrices, can be done by generating all the permutations of the numbers from 1 to 9. And this step 2, which is to check whether all the generated 3 cross 3 matrices in step 1 are forming magic square or not, what we can do is we can write a base case in such a way that we'll add that permutation in some vector only if it is forming a magic square, and we'll see how to do that. So basically step 1 and step 2 can be combined and implemented using recursion, and the code for that recursion will look very similar to the code for generating the permutations for the given set of numbers. And since we have already looked into how we can draw the recursion tree for the permutations for the given set of numbers or a string, I'm skipping this step 2 here. So next we'll look into how we can identify and write the function template. Okay, now let us look into how we can write the function templates. So here I have used three functions. First is magic square, second is generate perm, and the third is forming magic square. So let us start with this function, forming magic square. So this function takes the matrix S as the input, which is nothing but our input matrix S, which is of type vector of vectors, and its return type is integer because we want to return the minimal cost of converting S into magic square, which is an integer number. So this is the driver function, so it will call this function generate perm, which will generate all the permutations for the set of numbers from 1 to 9, or in other words all the possible 3x3 matrices. And later it will also perform some post processing, that is it will perform the step 3, which is finding the least cost magic square by comparing all the possible magic square which we generated with the input matrix. Okay, so this is all about forming magic square function. Next is generate perm. So as I said, this function will generate all the possible 3x3 matrices, or in other words it will generate the permutations for the set of numbers from 1 to 9 and will check which of them are magic squares. So the return type of this function is void because we'll store all the permutations in this matrix perm. So the type of this matrix is vector of vectors, and since each permutation is nothing but the array of integers, we'll need this vector of integer here, and since we want to store multiple such permutation, we'll need vector of vectors. And apart from this, it takes two more arguments. One is array, which is nothing but vector of integers or the array of integers, and this will store the numbers from 1 to 9, or the numbers or the set of numbers for which we want all the permutations. And the third argument is integer I, which is nothing but the index variable, and this integer I or this index variable shows the current level at which we are in the recursion tree. So we discussed more about this index variable I in the previous video, where we were talking about generating the permutations of all the permutations of the given string. So you can refer that video to understand more about this index variable I. Apart from that, there is this function is magic square. So this function checks whether the given input matrix is a magic square or not. So its return type is bool because it will return yes or no based on whether it's a magic square or not, and it takes the array as the input. So we are not providing the matrix as the input but the array as the input, because we'll supply the flattened matrix as the input rather than the two-dimensional matrix. So it will take the vector of integer as the input, so or in other words the array of integer as the input. So this is all about the function template. So basically we'll use three functions, and we'll now see how to write the recursive calls, that is the step 4. Okay, so now let us look into how we can write the recursive calls. So all the recursive calls will be inside this function generate perm, since this is the function where we are generating all the permutation for the set of integers from 1 to 9. So here we have this for loop where the integer j goes from the index variable I to the size of the array, and inside that for loop what we are doing is we are swapping the integer at the index I with the integer at the index j. Then we are making the recursive calls by passing arr array perms, that is permutations, and I plus 1. We are passing I plus 1 because we are going one level deeper inside the recursion tree. And then after the recursive calls we are swapping back the integer at the index I and j. So the entire logic behind this for loop as well as this recursive calls within this for loop and its correspondence to the recursion tree is discussed in the previous video, where we talked about generating all the permutations for the given input string. So you can check that out if there is any confusion here. So this is all about the recursive calls, and now we'll discuss about how we can write the base case and complete the step 3. Okay, so let us now look into how we can write the base case, that is how we can write this magic square function, and see how it fits inside generate perm function. and see how we can write this step 3 inside forming magic square function. So let us start with this is magic square function. So this function takes the matrix as the input and returns true if it's a magic square, else it returns false. So it takes the flattened matrix as the input and not the two-dimensional matrix as the input. So it takes the vector of integers and not the vector of vector. So it takes the flattened matrix and not the original two-dimensional matrix. So the first step, our first step here would be to convert this flattened matrix into the original two-dimensional matrix. So for that I have declared the matrix 3 of size 3 cross 3, which is named as matrix, which is nothing but the vector of vectors. And here I have converted that flattened array ARR into 3 cross 3 matrix using this code. So let us see how it is done. So basically we have this flattened matrix where we have 9 elements going from A0 to A8, and we want to convert it into two-dimensional matrix of this form. So basically our problem is that we want to arrange this elements A0 to A8 in this form, right? In this manner: A0, A1, A2, A3, A4, A5, A6, A7, A8. So for arranging them in this manner, what we need is some form of mapping, that is A0 should map to M of 0, 0, 0, A1 should map to M of 0, 1, A2 should map to M of 0, 2, A3 should map to M of 1, 0, and so on. A8 should map to M of 2, 2. So we need some mapping from the index I in this flattened array to the two indices which uniquely identifies the element in this two-dimensional array. And for doing that we use these two formulas, I divide by 3 and I mod 3. And I here is the index of the element in the flattened array. So let us try to understand this with example. So let us pick the 0th element, so that is the element with index 0 in the flattened array. So we'll pick I equals to 0 here, because I is 0 here. We'll place it here in these two formulas. So 0 by 3 is 0 and 0 mod 3 is 0. So we get 0, 0. So this indicates that A of 0 in the flattened matrix is mapping to M of 0, 0 in the two-dimensional matrix. Similarly, let us look into A of 4. So here I is 4, which is the index in the flattened matrix, and if we place it in these two formulas, we get 4 by 3. Considering the integer division, 4 by 3 is 1 and 4 mod 3 is also 1. So we get 1, 1. So A of 4 in flattened matrix is mapping to M of 1, 1. Similarly, A of 7, let us consider A of 7. So 7 by 3 is 2 considering integer division, and 7 mod 3 is 1. So we get 2, 1. So A of 7 in flattened matrix is mapping to M of 2, 1 here. So after performing this for each and every element in the flattened array, we get its corresponding position in the two-dimensional matrix. So in that manner we can convert this flattened array or the flattened matrix into the two-dimensional matrix. So this exact logic is being used here. So we iterate over all the elements in the flattened array and we place it inside the matrix at the appropriate position by using that two formula, I divide by 3 and I mod 3. So after doing this operation, after this for loop, we'll have our matrix ready, which is our two-dimensional matrix, which is obtained from the flattened array. Okay, so after doing that we need to assume a magic number. So here I have assumed the sum of values in the first column as the magic number. So that is what is exactly done here. So after doing that, if our matrix that we are currently considering is the magic square, then the sum of values in other rows, columns and diagonal should match with this magic number. So that is what is exactly done here. So here we are checking for the rows So we have this variable I which goes from 0 to 2, and for each value of I we'll check for that particular row. So when I equals to 0, we'll sum up values and we'll sum up all the values in that row, and we'll check whether it is equals to the magic number or not. If it is not equal to the magic number, then we'll return the false. Similarly for I equals to 1 and 2, that is, we'll check for the first and second row. So we'll check for the 0th row, first row, and the second row, and if any of the sum of all the values in any of the row is not equals to the magic number, then we'll return false. Similarly, we'll check for all the columns, and in case of columns also, I will go from 0 to 2, and for I equals to 0, 1 and 2, that is for 0th column, first column and second column, we'll check if sum of all the values within those column is not equals to magic number or not. If it is not equal to the magic number, then we'll return false. And similarly for both the diagonals. So if sum of all the values in those diagonals are not equal to the magic number, then we'll return false. And if everything is matching, then we'll return true at the end. So that was all about is magic square function. So now let us look into this generate perm function and how this is magic square function fits into this generate perm function. Okay, so for this problem, which is generating all the permutations for the given set of numbers, we hit the base case when the value of the index variable I reaches the size of the array. So we discussed this in the previous video when we were generating all the permutations for the given input string. So we hit the base case here, and when we hit the base case, we have one particular permutation in our hand, and we pass that permutation to is magic square function. And if this permutation is forming the magic square, then is magic square function will return true, and we'll store that inside this perms array, which holds all the permutations which are forming the magic square, and after that we'll return. Okay, so this was about how we can incorporate is magic square function inside the base case to find all the magic square and store them inside the perms array. Okay, so we saw how to write this is magic square function and how it fits inside the base case, and we also saw how the recursive calls are made here. So now let us move forward and see how the trivial function is written, that is how this function forming magic square is written. So inside this function, as you can see, we have declared the vector of vectors, which is perms, and which will hold all the 3x3 matrices which are forming magic squares. After that, we have also declared this array ARR, which is nothing but vector of integers, and it will hold all the integers for which we want to generate all the permutations. And after that, here we are populating it with the values from 1 to 9 because we want to generate all the permutations for the numbers from 1 to 9. After that, we are making this call to this generate perm function here, and after this call is being made, after this function execution of this function is over, this perms will contain all the 3x3 matrices that are forming magic square. After that, here we are declaring this integer variable mean cost, which will contain the minimal cost for converting the input matrix S into the magic square, and we have initialized its value with very high value or int max, and the corresponding magic square, the magic square corresponding to the minimal cost is stored inside this ANS, which is answer, which is nothing but the vector of integers, and essentially it's a flattened 3x3 matrix, which is corresponding to the magic square with minimal cost. Okay, so now let us look into how we can write the step 3 here. So step 3 here finds the magic square with minimal cost and store it in the array answer and its corresponding value in this variable mean cost. So let us see its implementation here. So we have this for loop here, and inside this for loop we have this variable index which goes over all the 3x3 matrix which are forming magic square. which are inside this POMs. So okay, so inside this for loop, what we do is we pick up the current 3x3 magic square which is stored inside POM of index, and what we do is we calculate the cost of converting the matrix as input matrix as into this POM of index, which is our current 3x3 magic square. So for that we declare this variable current cost, integer variable current cost, which is initialized to 0, and then we calculate the current cost of converting this input matrix S into the POM of index, which is our 3x3 magic square. So that is done here using this doubly nested loop. So here we have this variable I which goes from 0 to 2 and the variable j which goes from again 0 to 2, and inside it what we do is we take the difference between the matrices S and the POM of index. So there is one point that we should note here. We can, since this matrix S is two-dimensional matrix, we can index it using S of I comma j, but this matrix POM of index is the flattened matrix and it's not a two-dimensional matrix, it's a one-dimensional array. So in order to do difference between S and POM of index, because since one is the one is the two-dimensional matrix and another is the flattened matrix, what we need to do is we need some form of mapping in order to do the difference between these two matrices, and that mapping is given by 3 into I plus j. So let us look into how this mapping works first. So let us see over here. Okay, so basically what we are trying to solve here is that we want some sort of mapping in such a way that m of 0 comma 0 is mapped with a of 0, because we want to take the difference between m of 0 comma 0 and a of 0, m of 0 comma 1 and a of 1, m of 0 comma 2 and a of 2, m of 1 comma 0 and a of 3, m of 1 comma 1 and a of 4, and so on, m of 2 comma 2 with a of 8. Since this is because our input matrix S is in this form and the POMs of index which is our 3x3 magic square is in this form. So we need this mapping in order to do the difference. So okay, so in order to do that mapping we use this formula, as I said, I into 3 plus j. So in general it is I into n plus j, where n is the size of the row, but here since we have this 3x3 matrix, size of the row is 3, so it is I into 3 plus j. So let us see how this formula enables us to do the mapping. So let us work out few of the examples. So for 0 comma 0, when I is 0 and j is 0, we'll place 0 here and 0 here, so we'll get 0 into 3 plus 0, which is 0. So it says that m of 0 comma 0 is mapped with a of 0. Similarly, let us take this m of 0 comma 1. So we'll fit 0 and 1 here and we'll get 0 into 3 plus 1, which is 1. So m of 0 comma 1 is mapped with a of 1. So now let us also take this one, m of 1 comma 2, and see where it is mapped. So we'll place I equals to 1 here and j equals to 2 here. So we'll get 1 into 3, which is 3, plus 2, which is 5. So m of 1 comma 2 is mapped with a of 5. So I hope you are getting this. So the point here is that we are able to map the values inside this 2x2 matrix with the corresponding value in the flattened array, so that we can take the difference appropriately. Okay, so yeah, so we can index the input matrix as using I and j, that is we can do s of I comma j, and index the value which is corresponding to that s of I comma j inside this POM of index, which is our 3x3 matrix, which is magic square, and it is flattened using this formula 3 into I plus j. So this one and this one are the corresponding values to each other for which we want to take the difference. So we'll do it for each and every value, and obviously we'll take the absolute difference and we'll keep on adding this value inside the current cost. So after after taking differences for all the values inside this 3x3 matrix, both of these 3x3 matrices, will have the total cost of converting the input matrix as to perm of index, which is our current 3x3 magic square, inside this current cost variable. So once we have this value, we'll compare it with mean cost, and this is done here. So if the value of the current cost is less than the mean cost, then we'll set the current cost as the mean cost, and we'll update the answer array with this current 3x3 matrix which is forming the magic square. So that is about the answer and mean cost. So the point to note here is that we'll do this for all the 3x3 matrices which are forming magic square, which are stored inside this perm of index. And after this for loop is over here, we'll have the minimal cost for converting the S into magic square. I mean the value of minimal cost, or the value of converting S to the magic square inside this min cost, and the corresponding magic square to it inside the answer. So since in this problem we just want to return the value, we'll return min cost. Okay, so that's all, and that is how this function forming magic square looks. Okay, so yeah, that's all for this video, and yeah, I'll end this video here.